What is up, most distinguished patrons of this channel? So today we are going to dive deep into a viewer question regarding flow settings for shielding gas for MIG and TIG, etc. So that's what we're going to be tackling. Let's get into it. So this video is in direct response to a question that I got asked, and I actually get asked similar questions to this all the time, and that is regarding flow settings for welding. And I think a lot of this has to do with, well, how do you save money? How do you know if the flow is exactly what it should be? How do you know if you have inadequate flow? How do you know if you have adequate flow? So this is a pretty complex topic, but I'm going to simplify it by a lot. So the first thing we need to talk about is regulators. So the start of any kind of gas delivery system to your MIG or your TIG nozzle comes from, well, a tank of shielding gas and then a regulator or flow meter of some sort. And I have a video on flow meters and ones I recommend. I'll put a link in the description on a couple videos, but this I'm going to kind of cover everything again because this is completely intertwined with gas delivery. Therefore, I have to cover this, even though I'm going to be covering a lot to do with how to limit gas usage but still get good results. So you have two different types of flow meters that are common with welders. This is what normal welders come with. You have one like this that is a pressure regulator. This is pretty old school. That doesn't read actual flow. What this does is it makes an assumption based on a calibration that at X amount of pressure on the output means that it is this much flow or whatever. It's a calibrated flow meter in the sense it works off of pressure, thus pressure regulator. These are fine and work good to get close. The issue that I find with these, because you're not actually directly measuring the flow, what can happen with these is as you change shielding gases, the accuracy I find tends to vary far more because this is only calibrated. It says MIG, TIG. Well, this is calibrated for one gas mixture density. As that changes, I would imagine, and I've seen firsthand anyways, that the accuracy of this is all over the map. When you get into what's called a flow meter, where essentially you still have an initial pressure regulator just like this to drop the 2, 3, 4,000 psi tank pressure down to something usable. So you still have that in both of these. But this, you basically just open the output tap and a little ball rises in there, and wherever it stops is what your actual flow is. So this, you're actually measuring flow through a flow tube. The benefit of this, well, for one, it's far more accurate in my opinion than these guys, but this has multiple calibrations. Like it has pure helium, it has argon, and this one has CO2, and it says up to 40, so C40. I believe that's what they're referring to, CO2, argon. Yeah, so blend of gases there. So this guy can read accurate with multiple gases and multiple output levels. So across the board, I guarantee you this will be more accurate. Don't get me wrong though. These, especially the higher quality ones, tend to be fairly accurate, but honestly, you're going to end up wasting a fair amount of shielding gas by overusing shielding gas with this, to be honest. Now this guy over here is my personal favorite. It's a Model 355 Harris. They aren't cheap, but man, this thing works. It's accurate. It's beefy. What more do you want? I also like this guy, which is the Victor Cut Skill. This one is set up for shielding gases, and this came with my ESAB Rebel 235. This is also a great flow meter. No complaints with it. So part of consuming the least amount of shielding gas is accurately measuring it, which is why if you're concerned about that, it's in your best interest to get one of these. Now with that said, I don't care what regulator, flow meter, whatever you have, one of the things you can run into is what it says you're getting, you might not be getting. And that's where something like this comes in. What this is basically a calibrated flow tube, much like what these are, and this goes on your TIG nozzle or your MIG nozzle, and it will tell you what the flow rate is coming out of it. Now, one thing to remember with this is that this is calibrated for some specific gas mixture, and I don't know how accurate this is. However, if you test this in comparison to your regulator and you don't have any leaks, you'll at least be able to get a ballpark figure of what it should be. This is a very handy troubleshooting device if you're welding and you're getting porosity in your welds, like your MIG welds, and you can't figure out what's going on. If your regulator says you're getting 40 CFH and this says 10, well, there's no real wearable parts in here, so this probably isn't lying. That means either your regulator's shot or you got a leak in the system. So for troubleshooting, they're very handy, but it can also tell you what's kind of getting to the nozzle. Now, in my experience, I find that that's pretty close, within 2 CFH roughly of what the higher end regulators I have say. So I would say they tend to be pretty accurate. Now, let's talk a little bit about the gas shielding, and we'll start with MIG first. So this is a MIG gun, and it might be a little bit different than the one you have. This is a Spraymaster 250. This is set up for higher amp, higher duty cycle, so the parts are probably a little bit bigger than what you got. Yours may have a thread-on nozzle, it may clip on, your contact tips may be held in by the nozzle. There's all sorts of different types of these, but what you need to understand is this is a pretty simple device. You basically have a MIG whip, which is this rubber-covered hose. Inside of there you have an electrical wire for the contactor here for the switch. You have a hose for the gas shielding to go up through this, and then you have a power wire that hooks to this. That power wire hooks to this contact tip, basically this part right here, which makes the contact tip live to where when you pull the trigger, all the current from your machine is present here, and then thus you can weld. Now, the gas ports on this, where the gas escapes, is right here. There's 3 or 4 of them on this. Yours may have a little bit different of a setup. This gas nozzle slips on. There's an O-ring here and a back cap. That's to keep the gas shielding going out the nozzle, which has no restriction because there's no crap in it, and well, that's how this works. So your gas shielding comes out here. Now, your setup may have different gas ports, but universally all MIG welders are just like this, very similar. Now, the limitation on shielding gas with the MIG process is because this shielding nozzle gets so much spatter in it and gets so filthy, you're very limited to what you can use to allow gas shielding through here. Now, with the TIG process, you can use gas lenses that more or less create a laminar flow where the gas comes out in a nice smooth column. That allows you to have better shielding with less flow. This is more or less a turbulent gas flow coming out of here, which unfortunately requires you to use more shielding gas than what you would normally have to, like with TIG, simply because the shielding provided by this with gas is very limited. Now, there are still ways to save on shielding gas usage, and that's something I'll talk about once I show you the TIG components. So let's look at those. Here we have a TIG torch, and I currently have a stubby gas lens installed. This functions somewhat like the MIG gun and the MIG whip. This hose is both a power cable and it has shielding gas that runs through it, and then the shielding gas comes up through this head, out through the gas lens in this case, with that mesh filter on it. Same thing like this is a gas lens, just a larger one with a mesh screen. The whole purpose of these with a TIG torch is to create a laminar flow column of shielding gas, so you can run a longer tungsten stick out, and it just provides better shielding regardless of your stick out, so your welds don't oxide as much, especially critical with stainless steel welds. Now, conventional TIG torches don't use these gas lenses. They use what's called a collet body. This collet body more or less threads in, and it has ports for shielding gas, just like a MIG gun. It's basically the same thing. And then you take your ceramic cup and thread it on there, and the gas simply escapes around, out of these holes around this and out the front because, well, it's not plugged or anything, so it's at zero pressure. These Standard cups and collet bodies are fine to learn on, but you can actually reduce argon or shielding gas consumption significantly by using a gas lens, because again, you can lower your flow but maintain proper shielding. And here, by the way, is a stubby gas lens, so you can also get these a lot smaller typically than what you would find with a collet body. So I think you understand all this stuff. Let's talk a little bit about how much shielding you really need and how to cut back to save yourself some money. So I made a little cheat sheet here for me so I make sure I don't forget anything. So when it comes to gas usage, let's talk about MIG first. So gas shielded wire process, just straight MIG, so not dual shield or anything else, 15 to 35 cubic feet an hour gas flow. That's a very broad range, which means that if you're running at 35 plus cubic feet an hour and you only need 15 to 20, well, you're just pissing in the wind, buddy. You're wasting money for no reason. Now, I'll get into how you know if you're pissing in the wind per se, but for right now, that's our range that we're going to talk about. Now, there's a multitude of factors that will change whether or not this is more or less than average, so say 20 cubic foot. Your weld position and the weld type matters hugely. In front of me, I have a fillet weld here that's TIG aluminum. Yeah, we're talking about MIG, but whatever. So when you come in here at your MIG nozzle, this functions as a dam or a shield to keep that shielding gas in the weld pool area. And since most shielding gas mixtures tend to favor the heavier than air, it will sink and sit there, and you tend on a fillet weld to have very good gas shielding at reduced shielding gas flows. So if you're doing a lot of fillet welds, you're probably wasting a lot of shielding gas if you're running real high flow. Again, it depends on a multitude of factors, but a fillet weld, less flow. If you have an outside corner joint, which I really don't have one, but picture this is just lopped off here, so you have an outside corner joint, that tends to split the shielding gas, not to mention if the gas is heavier than air, it's going to want to sink. And oftentimes on an outside corner, you're going to want to maintain higher shielding gas flow in order to get proper coverage. And in a case of MIG, you won't have porosity. In the case of TIG, oftentimes your welds just look like crap, gray out, and the molten pool doesn't flow well. So the weld type matters hugely as far as what gas is the minimum you need. The weld position also matters. If you're welding vertical up, especially in an outside corner joint, you may need more of a minimum gas set point than say a flat weld or just a lap weld, a bead on plate, whatever, in a flat position. So that plays a factor as well. Now the material plays a factor. Welding aluminum, in a lot of cases, at least with TIG, you can get by with a little less gas flow because of how fast the metal solidifies. With MIG aluminum, you're still going to need pretty high gas flow. Otherwise, you're going to start getting major soot or porosity issues because that process is quite a bear to run if anything goes wrong. Like, that's not one to try and save money on shielding gas, to be honest. But the material matters. Now, stainless steel requires far more shielding gas with the TIG process and arguably MIG. Well, it requires more expensive shielding gas with MIG to weld properly. So the material is huge, and also not even listed on here, the standard that you have to meet for the finished weld will play a role in how much shielding gas you need to run. And the reason I bring that up is with stainless, or even better, titanium, if it has to meet a specification of no oxide colors, especially on titanium, you're going to need to bump that cubic foot an hour up sky high with a lot of flow in order to meet that. So that plays a role as well. With the short circuit MIG process, your contact tip to work distance or to the weld pool distance tends to be about 3/8 of an inch is what you should be aiming for. Because it's so short, you generally don't need that high a gas shielding. Now, when you start talking dual shield or spray arc where you're running longer stick outs, where it's quite a bit out of the nozzle off the contact tip, those you have to run higher shielding gas flows, because what will happen is you'll get porosity because the shielding gas isn't reaching where you need it to. So The stick out distance with MIG is critical, that depending on the process you're using, that you may have to bump the flow up. Now, amperage plays a role in that as well. When you get into processes with wire that run higher amperage, like dual shield and spray, or even just very high values on short circuit, short arc MIG, you can run into issues where the gas shielding is not sticking around long enough, and the red hot metal is still red hot, and as it's solidifying, it's being exposed to oxygen because, well, the heat is so high, the weld is liquid, and you're already motoring on here, and the area behind your gas shielding is still red hot. Therefore, increasing shielding gas increases the amount of shielding gas in the area that's covered, and it will help reduce oxidization and porosity of the weld. The process also matters hugely. In the case of TIG, for most things, you're going to be in around 15 to 20 cubic foot an hour with a standard collet body. With a gas lens, somewhere around 15 cubic foot an hour would be a good baseline. So the process of TIG tends to use far less shielding gas than MIG, again, for the reasons I mentioned earlier in the video. The gas type also matters. If you're using helium with TIG, guess what? Helium's lighter than air. You're welding here, gas is escaping around your cup and it's not getting towards the weld, so you have to run higher flow rates and more, just for the sake of it's lighter than air. And you can also run shorter stickouts to try and help with TIG, but it is an issue, like you have to run more flow. Now with MIG, there are gas blends that have a large amount of helium in it, like for stainless steel. Guess what? That gas blend needs higher cubic feet an hour of flow to get proper shielding. So gas is also a huge role player in this. Now let's talk about how to cut back on flow rates. So you want to save some money on the gas usage with the MIG process. Here's a list of things that should help you. Number one, your gas nozzle, if you don't keep it clean and it's full of crap, that's going to affect the gas flow, the turbulence out of it. Now, don't get me wrong, it's always going to get that BB spatter on it. But if you have big chunks in there and the gas is coming out squirrely, guess what? You're going to have to run higher gas flow to get proper shielding. So keep your nozzle clean. Number two, your contact tip to molten puddle distance should be about 3/8 of an inch. Now this nozzle actually sticks out quite a bit past the contact tip. It's already about 1/4 of an inch. So this is meant more for spray. Therefore you can kind of cram the nozzle in there and you maintain that 5/8, 3/4 inch stick out depending on how much voltage and amperage you're running for spray. So this is more suitable for that. But if your MIG nozzle is not level with your contact tip, you may want to consider grinding this down to make them level and then pushing that contact tip, this whole assembly, into the weld as close as you can get into the joint. Therefore you can maintain a short stick out, therefore you can run less gas coverage. Another very, very important thing, you can't have leaks in the system and expect to have good results. If your nozzle O-rings are bad, blown out, or missing, guess what? Some of that shielding gas is going to escape and it's not going to make it to the weld. Likewise, if you have leaks in any part of the whip or at the machine, remember guys, the machine has numerous O-rings typically in it, or the gas valve itself inside of the machine. If the hose has leaks because it melted, or who knows, like if you have weird porosity issues and you can't figure it out, you cannot have leaks in the system. So fixing that or making sure that all the O-rings are fresh will make a difference in the long run, especially if you got an older machine that's been ridden hard. Obviously this goes with all welding processes, but if you just arbitrarily adjust your flow meter and whatever it says is what you're getting, well, guess what? More accurate flow meter might actually help you. And speaking of the gas flow, a lot of higher end MIG welders have what's called pre-flow control. That's how much time is spent where the gas valve is open before it starts feeding wire and initiating the arc. If you have too low a pre-flow, what can happen is the start of your weld has porosity because the gas has to make it all the way down the whip, out the nozzle, and to the molten pool before it reacts with oxygen. Well, if you adjust it higher, you may be able to run lower overall cubic feet an hour and still get acceptable welds. What can happen is that if you have no pre-flow or very low, you might have to set the cubic feet an hour on your flow meter higher just to get a faster push of shielding gas to prevent porosity at the start of a weld or during it. So that's something to consider as well. Now, joint style matters, like I said. If you're welding fillet welds, experiment and drop the flow a little bit until you start seeing porosity and then bring it back up. I mean, the biggest problem is that if you drop it too low, you're going to have undesirable porosity and weld defects. The puddle won't flow well, and it's going to typically look grayed out or nasty looking, and those are things you generally don't want, so there is a lower limit on flow. But if you know you're doing fillet welds, back it off a little bit. If you're doing outside corner joints, bring it up a little bit. If you're doing an outside corner joint or something like this, where you know it's going to split the coverage, if you put something like this bar here and clamp it to what you're welding, guess what? You just more or less created a dam for the shielding gas to sit and protect your weld, and it also pulls heat out of it, which is good in the sense that you can use less shielding gas because a molten pool turns to solid faster. All things to consider. Now let's talk about TIG. With TIG, the number one thing you can do to save on gas usage, get rid of this collet body garbage. I'm not joking, guys. I mean, maybe for welding aluminum you could use that, but everything else, use a gas lens, and preferably get a CK or one from Weldmonger, aka Jody, which he uses CK anyways, or a Furic cup, any of those. Get a name brand one. They're better in my experience. I mean, this right here is a generic one and it's okay. It's better than nothing, but you can cut your gas usage on steel in half with one of these. And even though this is a bigger lens than like this collet body, okay, the gas shielding is better because of the laminar flow, or the lack of turbulence works so much better, and since argon is heavier than air, it sinks. And on most joints you can run, in my experience, somewhere between 10 and 14 cubic feet an hour up to about 160, 180 amps with one of these, versus if you're using a collet body, you're going to get poor shielding with that at 15, 18. Even 20 sometimes. So get yourself a gas lens 100%. Now your stick out obviously matters. If your stick out is a mile outside of the cup, even with a gas lens, you're going to have to run more shielding gas. If you put that in there quite a ways and you're able to weld with it barely sticking out, guess what? You can cut back your gas flow down to 10, 9, somewhere in there cubic feet an hour at 120 amps. So stick out matters hugely. Another option you have is to use a smaller cup. If you're using a number 10, a number 12, where it's a lot wider than this guy, guess what? You need more shielding gas. And the only time you generally need cups that big is for welding titanium and Inconel and stainless. So if you're just doing fillet welds on steel, get rid of the big cup and stick with a number 8 or a number 7 with a gas lens. You'll cut back your usage significantly. Pre-flow control also matters with TIG. If you don't have any pre-flow or low flow, what can happen is you have to run higher initial gas flow in order to get the results you want at the start of the weld, or you can burn up your tungsten or have porosity issues as well. There's another way that's better than probably everything I mentioned as far as saving money on gas usage. Let's talk about that. I always found it funny when people asked me how to save money on their shielding gas, and then when I told them to buy a bigger tank like that, oh, I don't want to do that. It's like, well, take a look here. So that's like a 300 cubic foot or 330, whatever it is, the big one. And then take a look at this little guy here. This little tank, which is probably like, I don't know, 20 cubic foot, I bet that sucker to swap out would cost me 30 bucks maybe. I don't even know, somewhere between 20 and 30 bucks. This 300 cubic foot cost me $75. You do the math on that. Actually, I did it for you. I'll put it up right now. So now this chart and information is going to be accurate to my area. Where you're at, you may pay a lot more than what you see here, or even possibly less. And of course, you always have the option of buying a used tank. If you do that, make sure that it's in test date and that it's actually an owner tank and not a lease tank. You can run into all sorts of trouble if some idiot sells you basically what amounts to a stolen tank, where they lease it from someone and pay a monthly fee, and then they sell it to you for half price or full price, and then you go and try and swap it out, and then they take it and won't give it back to you. All sorts of issues on that, so be careful. Anyways, when you look at the cost savings, if you weld 24 hours worth of actual welding time in a calendar year, you will break even on the cost of going to a big cylinder. Now, I understand the big cylinder isn't very portable, so that's an issue in itself. You might not be able to fit it in your vehicle. That's also a potential issue. But the cost savings, I guarantee you, is going to be huge no matter where you are. So if you can afford to get a bigger tank in the long run, it's going to be worth it. Now, 24 hours of welding might not sound like a lot, but you'd be surprised at how fast you burn through that, especially if you're learning. I mean, in school, I burned through at least that much shielding gas, 24 hours worth, in a matter of a few weeks when you're welding 3-4 hours at a crack. And if you're practicing or have a lot of projects, it's a no-brainer. Get the bigger tank. So as you can see, the bigger cylinder is massively cheaper when it comes to argon and for shielding gas blends. There's no comparison between the bigger and the little tanks. I have a little tank simply for a backup for when this is empty, which it happens to be empty right now. I need to swap it out. So buying a bigger tank will save you so much money in the long run. Unfortunately, they cost a lot more money. There's a lot of ways that you can save money on that by picking up somebody else's tank. I'll have to do a whole video on that because you can really get screwed on deals like that. But anyways, you can save a ton by getting a big tank. That's what I would recommend. Let's talk about a couple other things. I did a video on CO2, 100% CO2 gas versus C25 with the MIG process in the past, link in the description. But if you're MIG welding and you want to do a ton of practice, or you just want to weld stuff together and you want more economical shielding gas, get 100% CO2. It's almost as strong as using C25 gas for performance of the welds. And this tank, which is a 20-pound tank, it's given to you as a liquid and it's in pounds. 20-pound tank is equal to somewhere around 160 to 180 cubic foot cylinder, and it's $15 to $20 Phillips. So this thing is over half of that big blue tank for $15 versus that is 75 or 70 or so. And you can see two of these at maybe 30, 40 bucks is half the price of argon or half the price of C25. Now keep in mind, you can't use this with TIG, but I'm just giving you a comparison in gas costs. You can make the MIG process extremely economical by using 100% CO2. Not to mention, this tank isn't very big and holds the equivalent of 180 or so cubic foot of gas. Very compact, portable, very handy to have versus trying to lug around a 150 cubic foot cylinder or a 300. This is very easy to transport. Now let's talk about signs that you don't have enough gas shielding. Obviously, it's in everybody's best interest to waste as little of gas as possible, but the reality is welding in general, it's better to run a little bit more than you need and then be covered for variables than to run the absolute bare minimum and then have issues that pop up. If you run enough of a certain type of weld, you can keep backing the flow off until you start getting evidence of defects like porosity or really grade cooked looking welds despite not running a lot of amperage, and then you can just bring it up 2-3 cubic foot an hour and you're fine. So that's always an option. But for you and me that do a lot of random jobs around the place, the question comes, well, how low is too low? Experience will help tell you that with your machine and your flow meter. But the truth is that you have to go by what you're seeing for defects. So if you see porosity, if you see discoloration, anything like that, or if you notice like at the start of a weld, it doesn't fuse very well and it sputters. If you see excessive spatter, like here where there's a ton of spatter in there, and that's kind of a bad example, but excessive spatter could also be an indication of gas shielding problems. And if you see that, bump your cubic feet up a little bit. If you're already at like 20 cubic foot an hour and you're seeing weld defects, you probably have a leak, the wrong shielding gas, or your flow meter's trash. So at 20 cubic feet an hour on a flat or a fillet weld, you should be able to make decent looking welds. Something else is wrong if you're having issues with that, like the wrong polarity, for example. Now, if you're going to weld on critical type stuff, so in the case of TIG, titanium like this, or stainless, you have to use more gas shielding. Not only does improve gas shielding, so bigger cup and higher flow rates, it improves the weld pool, so the weld pool's nice shiny silver, it reacts consistently, it doesn't react with oxygen, and in the case of titanium, any color, any oxide color on titanium, the weld is junk, it's brittle. You squeeze it and it sounds like ice breaking, it's junk. So titanium is one of those materials where you have to use a big gas cup, you have to use a ton of flow, and that's why you really can't MIG weld this stuff that I know of, simply because the gas shielding issue is too much of a problem with this. TIG is the way to go with titanium, and typically Inconel and copper nickel and all those. But critical stuff, up the flow, it's not worth the risk of weld defects. Now for practice, by all means, if you're trying to do a bunch of fillet welds or something, like this junk, I don't know where this came from, by the way, but if you're trying to do a bunch of these, 100% lower the flow to as low as you can go before you get defects, and then bump it up 1-2 CFH and run it. Save yourself the money. For critical jobs, paid jobs, bump it up a little bit, take pride in your work, it's all right. You know, you just don't want to be 10, 20 cubic feet higher and just wasting all that argon flow, even if your boss is paying for it. Don't be a moron. Not that you need to save them money. Be respectful of the argon. I mean, that's part of the reason why we're in a helium shortage, is because people were using it like it was going out of style. And now, next thing you know, you can't get the stuff and it's $500 or more a tank. Well, anyways, not to go on a rant about that. So I think I covered this stuff pretty good. You have a pretty good idea what's going on. Let's go to conclusion. So I'm sure I forgot something. There's always more to know, and my brain is only this big, so I can't recall every little aspect. You learn so much when you just do stuff and react to issues that arise, and if your gas flow is too low, you'll know, generally speaking. But with that said, I think I covered this pretty good. Feel free to include any other thoughts you have on this down in the comments, and anyone watching this video, please read the comments, because there's a lot of truth and great ideas in those. And this channel happens to have some of the best comments around, where people are really helpful and like helping, and really good people, and that goes a long way. So trust me, listen to what other people have to say on this if you're trying to save money. But honestly, my opinion is, get a decent flow meter, or at least check the one you have. Do everything like I said in this video to minimize gas usage, and stop screwing around with the little cylinders unless you're 100% CO2. Get yourself a 300 cubic foot cylinder. I know they're expensive, but if you plan on welding a fair amount, aka for 3-4 years or more, and you might make money doing it, you will not regret buying a big cylinder. The cost savings in a year span, I mean, for me, in 1-2 months, the savings pays for itself. So for you, probably not so much, but I get at least 150 cubic foot or a 125 cylinder. Don't screw around with the little portable ones unless it's an emergency backup. So with that said, hopefully you learned something and you enjoyed the video. Until next time.